community. Hey Bob, would you hold it?
Can you hold it? Can you hear it better now?
There you go.
Yeah, I have a weak voice. He has been involved in various research projects throughout the time concerning topics such as nuclear thermal propulsion, which we'll hear about hopefully, space radiation phenomena, radioisotope power systems. He currently works as a staff member at Oak Ridge National Laboratory in the Reactor and Nuclear Systems Division, where he serves on multiple space-related and NASA-funded projects. Prior to his transition to nuclear engineering, Michael worked for the maritime industry from 2001 to 2016 in various capacities as a commercial diver, boat captain, and manned submersible. So, you're going to talk any about that? I think a lot of us saw part of this kind of talk. He said there'd be some new stuff at the Orion about a month ago, something like that. Oh, a few months now. Okay. Yeah. Michael Smith, thank you. Thank you for coming.
All right. So first off, thank you again for the introduction and thank you for having me. My name is Mike Smith. I work at Oak Ridge National Lab currently, and I deliberately go out of my way to try to stay as actively involved in the space community as I can. That is my passion. That's what I love to do. And so I have thus far been lucky and been able to do that. And so today I'm going to talk to you about some of the projects that I've been involved with at Oak Ridge in support of the space community. So specifically, just a little bit of background, the type of work that I do, I am not an experimentalist, so we do a lot of simulations in our group. We do a lot of radiation transport simulations specifically of space flight scenarios having to do with both natural radiation and man-made radiation from spacecraft power systems or propulsion systems. So, the talk today, I know you all are quite a scientifically literate crowd, but we are going to go over some of the fundamentals. I'm going to give a brief overview of some of the topics that I'll be talking to you about today. And I know there's a handful of people that may have been at the Orion talk that Bob was talking about a few months ago. And so if you were there, this is a recycling of that talk, although there has been a couple what I think are interesting projects that we've been able to add to that since then. So if you saw that talk, thanks for listening again, and I hope you enjoyed the new information. So as far as this talk, what I like to clarify first, if you are unfamiliar with the synergies of nuclear engineering and aerospace engineering or sciences, I like to start here. So a lot of times when people hear the term nuclear, depending on the crowd you're from, you may envision nuclear reactors, terrestrial nuclear reactors, and then if you hear of space sciences or space engineering, you may, depending on what era you're from, think of the shuttle era, International Space Station, the Apollo program, but a lot of times people don't know or aren't aware of where these two disciplines overlap. So to kind of break that, as far as I see it at least, the taxonomy of what I call nuclear space sciences down and how nuclear engineering can support the aerospace industry, these are kind of the three main branches as far as I see it. There's the study of radiation, both from naturally occurring space radiation and then power and propulsion systems. There's the generation of power for spacecraft, whether it be from decay heat or fission heat. And then there's propulsion itself, which can be generated either through what is known as nuclear thermal propulsion or even what is known as ion or electric propulsion. So the areas that I work in that are related to these little sub-taxonomic groups here mostly reside within the radiation simulation and transport of radioisotope power systems, and then I dabble a little bit in nuclear thermal propulsion. So this is the part of the talk where I'm going to go over a brief overview. If you're unfamiliar with what these specific topics are, I think it's important always to kind of put everybody on the same playing field, give you a brief background of what they are before I talk about the specific projects that we're doing. So, radioisotope power systems. If you are unfamiliar with how these systems work, in a nutshell, you take a radioactive isotope that is emitting some type of particle, let's say plutonium-238 that's emitting alpha particles. Those alpha particles stop or attenuate in the fuel meat and cladding material. They generate heat, and you can exploit that heat to do things like make electricity with. Plutonium oxide that is flight qualified generally puts out just under ½ a watt thermal per gram. So this is in the oxide compound. The specific isotope that we'll be talking about today will be plutonium-238, which many of you all I'm sure are familiar with, that we do make currently to support the NASA RPS program, Radioisotope Power System, RPS. So Pu-238 is currently being made at the high flux isotope reactor. at Oak Ridge National Lab to support the RPS program. So what do we do with this half-a-watt thermal program? So what you can do is you can just use it as heat, right? So there's a number of missions that use plutonium oxide only to keep some temperature-sensitive component on a spacecraft warm, nothing more. The next step up in complexity, I would say, is where you start to convert that heat into usable electricity. Typically and historically and currently, the state-of-the-art is we use thermoelectric materials. It's a a solid-state conversion process exploiting what's known as the Seebeck effect, where you can quite literally generate a charge just by having a very specific combination of materials spanning a cold leg and a hot leg, and you can start to generate a voltage which you can then exploit on a spacecraft to power an instrument suite, to use propulsion on a rover, or to generate propulsion on a rover. Right now, the state-of-the-art flight-qualified system-level conversion efficiencies for radioisotope thermoelectric generators is on the order of about 6 to 7% conversion efficiency. There are lab demonstrations of upwards of 10 to 14% conversion efficiency. But as far as system-level flight demonstrated conversion efficiencies, we're in the neighborhood of 6 to 7. So 6 to 7. And then the next step up in complexity is when you start to use heat engines, right? You take this same heat, you just apply some thermodynamic cycle to that to exploit and make electricity. So the conversion efficiencies of some of the state-of-the-art Stirling converters are touting efficiencies upwards of 30%. These are benchtop demonstrations. We expect once this kind of settles out as far as a system-level conversion, we're expecting to see a neighborhood of 20, which is phenomenal, a huge increase, right? So a factor of 4 kind of return on the power that we painstakingly go to generate at Oak Ridge. And currently, we're just dumping 95% of that heat to space or to the atmosphere. So this is a, albeit more complex system that brings with it its own inherent engineering issues, a better exploitation of that thermal energy. So if you are unfamiliar with how this all started, I think it's kind of important and fun to start with the trivia. So why did RPS come around? And this trivia question, I'm assuming somebody in this audience knows that there was an important space event that occurred in 1957. Yes, right, exactly. And so Sputnik was launched, it went into orbit, and we were freaking out, right? And so in an attempt to try to understand and map the orbital elements of Sputnik, scientists in the U.S. devised a very clever means of using what's known as a Doppler broadening shift of the radio signal that was coming from Sputnik. You could tell a slight difference in when the orbit was approaching your stationary receiver on the surface of the Earth versus when Sputnik was moving away from it. And you could use this subtle Doppler shift to determine where the satellite was in orbit, right? So we could map their orbit. So not long after, some very clever people in the Navy realized that we could invert that problem and use that same phenomenon to understand where our ships were by placing transponders on the satellites and then receiving the signal on Earth. So the transit satellite system, which is the precursor to the modern day GPS system, was instated and sort of brought the need for us to have a more sustained power ability in orbit in space. A lot of the photovoltaics of this era were still in their infancy, so radioisotope power systems offered a great robust solution for low Earth orbit environments for sustained satellites. So as far as the history from there, the door was opened in 1961 with the first launch of a radioisotope power system. And then the floodgates were open, right? That was sort of the proving ground. Things went great. There had been tens of missions that have been launched since then successfully using radioisotope power systems as the primary, not an auxiliary, but the primary power system. And they're actually absolutely phenomenal and have helped provide a power generation platform that has supplied us with much of the information that we know about deep space science and planetary science. And so this, excuse me, this is a recently named mission. If you haven't heard about this, this is called Dragonfly. Go Google it. It's very exciting, very interesting. This is an octocopter that will use a radioisotope power system to fly around Titan, one of the moons of Saturn, in my opinion, one of the most exciting missions that we might get to see. The current scheduled launch date is notionally in 2026. And so that's your background on radioisotope power systems. Space radiation. I'm talking about naturally occurring space radiation here. So if you are unfamiliar with space radiation, our understanding of it, space radiation has been around since the dawn of time, right? But our human understanding of it kind of came into being in the era of Marie Curie right here. So she specifically wasn't researching space radiation, but this is when we started to be studying the phenomenon of detecting, understanding, setting up laboratory experiments, studying radiation phenomenon, right? So one thing that was noticed while we were in the infancy of nuclear engineering and nuclear physics was the concept of background radiation, right? You could do an experiment here, and you get, some number, right? And then your colleague or whoever does the exact same experiment over there, and they get some different number, right? So we started to understand there's this concept of background radiation that at least partially is due to naturally occurring elements, unstable elements, in their respective decay chains here on Earth. But there was another unanswered phenomenon. There was a lot of speculation about the concept of extraterrestrial sources of background radiation. And there was a number of different experiments that were conducted. People went up in the Eiffel Tower with these, I guess now what we would call a primitive electroscope, which was just an older style of radiation detection equipment. And Victor Hess conducted a series of experiments in a hydrogen balloon, mind you, where he flew, quite literally, up to the neighborhood of 17,000 feet in altitude himself. And his team, they would go up and take a whole suite of electroscopes and take measurements, right? And so they were actually trying to prove the fact that background radiation was mostly terrestrial. And so the assumption was the higher that they were going to go, the green line right here, the lower the background was going to get. And then, this is what's fun about science is, it turns out the reality was the higher they went, the higher the background radiation got. So this kind of ushered in a whole new excitement and study of this extraterrestrial source of background radiation. So now, fast forward to 2020, we understand there's a lot of subtle nuance, a lot of sources of background radiation from space. We can't just say space radiation in general. So this is my, again, kind of breakdown of the taxonomy of naturally occurring space radiation. I declare that there are three primary sources: galactic cosmic rays, solar particle events, or solar energetic particles, depending on what discipline you're from, and then trapped radiation belts. And then, of course, you can dig down into the nuance of each one of these. But in general, the ones that we'll be talking about today, I definitely want to touch on galactic cosmic rays. So, if you are unfamiliar with galactic cosmic rays, in a nutshell, it's, in my opinion, one of the most interesting and exciting phenomenon in the universe. It's basically the periodic table from hydrogen up to uranium being ionized and accelerated like a particle accelerator and ejected out isotropically in all directions, coming from everywhere and going to everywhere, roughly since the beginning of the universe and roughly till the end of the universe, creating this low-density, dissociated plasma state throughout the universe, right? And so this is the raw galactic cosmic ray spectra, but here we reside inside the heliosphere, or the magnetic bubble of the sun, right? And we're kind of plowing through this low-density plasma, right? And something interesting about our sun, it does not have a constant magnetic rigidity. We kind of ebb and flow on a roughly 11-year solar cycle. And so when the magnetic intensity of the sun is at its minimum, there are more charged particles from the galactic cosmic ray spectra that are allowed into the heliosphere. Conversely, when the electromagnetic intensity of the sun is at its maxima, there are less particles in here. So it is not a constant phenomenon, it ebbs and flows. So that's galactic cosmic rays 101. So that's stuff coming from outside the heliosphere inside to Earth that we're concerned about. Now, conversely, we also have to contend with our local sun here, which is, as we were just alluding to, kind of unstable and does all sorts of interesting things, like emitting large waves of charged particles like protons, helium. Depending on the type of activity, these are much more anisotropic, meaning they're directional. It's like a shotgun blast out of the sun, a shotgun blast on the order of the size of a planet. So, when you're kind of in a solar particle event, it's relatively isotropic. When you look at it on this scale, it's quite anisotropic and directional. But nonetheless, we have to contend with these when we're looking at space working environments from a radiation perspective. There's been a number of documented historical events, and we expect many more to come. The last type of radiation that we'll be touching on that we typically bring into conversations when we're doing analysis with NASA or DOE or whoever about space radiation phenomenon is trapped radiation belts, right? So we were alluding to these magnetospheres. Earth has a magnetosphere. Jupiter has an insanely intense magnetosphere. Saturn has a very intense magnetosphere. Uranus, Neptune as well, and also along with the Sun. This is an image of, on the left over here, these are the proton fluxes. These are the electron fluxes. In reality, of course, these are overlaid in synergy with one another, but here they're just separated to show you kind of the relative levels of each one of them. And then this is a major point of contention when we look at any kind of robotic missions. We're not looking at any manned missions anywhere near Jupiter anytime soon. So this largely comes into the discussion when we talk about robotic missions, largely to the moons of Jupiter or Saturn now. Yeah, so trapped radiation belts. So just to kind of wrap a bow on the space radiation stuff, I always think it's important to show some comparisons about dose rates, right? So if we wanted to look at order of magnitude comparisons about what you care about and when, I think it's important to look at these side by side, right? So these are in rem per hour. So if we were to pretend to stick a person in the orbit of Jupiter, in orbit around Jupiter, around the orbital radii of Europa, one of the moons of Jupiter, you're getting on the order of, 1E5, 1E4 kind of rem per hour. This is very orbital radii specific, but it is in radiation terms, a screaming hot radiation area, a place where you don't want to be unshielded. So now flipping this over into linear scale, right? I think it's good to show the order of magnitude differences here, but this is what really shows you, if you're doing a mission to Jupiter and you're modeling radiation, you're concerned about the radiation around Jupiter first, right? And so now we'll throw Jupiter out of there. Let's say we're going to Mars, right? And let's say we've got a radioisotope power system. What you want to be concerned about if you're in close proximity, this is a dose measurement from the power system that's on Mars Science Laboratory's Curiosity rover, 1 meter away radially from the power system. You can see that this dominates at least the biological dose rate of a mission that you're going to be concerned about if this were a manned mission over background space radiation. Scaling the y-axis, removing that dose, you can see that if you're comparing Earth surface background radiation rates with deep space versus a lunar or Martian surface, that your deep space is kind of the driver of your dose rates. So anyway, I always think it's important to try to show these side by side to show you how we kind of try to scale what we worry about most when we're starting to dive into one of these problems.
What's the danger point for us, for man?
Yeah, well, okay, so it depends, right? And so we have acute radiation dose data that is from criticality accidents, bomb survivors, and a handful of other radiological accidents. When you start to get into, so dose rates versus acute doses, there's kind of a gray area between these, right? So these are sustained, long duration, elevated dose rates. Tens of rem is when you can start to see in an acute level some immediate response, negative physiological responses, right? Hundreds of rem is when you start to have significant die-off in significant percentages, and that's in an acute form. If you spread that 100 rem out over the course of half a year, 1 month, again, the data to support the effects in humans are lacking at this point as far as sustained elevated dose rates. So I'd say tens of rem acutely is where you start to really have an issue acutely. Yes?
Where the space station would fall in there?
Yeah, so space station is actually, well, okay, so it depends, right? It depends. So in the space station, we're actually interacting with portions of the Van Allen belts. So it's actually a little bit elevated above what I would call deep space. So you get most of the galactic cosmic ray spectra, but you also, at around 200, 300 kilometers, you're cutting down a lot of the solid angle that you're viewing the raw galactic cosmic ray spectra from, but you're elevating it because of your exposure to some of the Van Allen belts as well. So it works out to where it's a little bit above background space radiation in deep space. but it depends because there's also weird phenomenon. Our magnetosphere is not a uniform distribution. There's holes in it. For lack of a better term, there's what's known as the South Atlantic anomaly. And when you're passing through that, you can have a depletion of Van Allen belts and an increase of your deep space radiation exposure. But on average, it's a little bit more than being in deep space. So moving on to the brief overview of nuclear thermal propulsion. If you are unfamiliar with nuclear thermal propulsion, I think it's kind of exciting that some of the first mentions of ever using nuclear reactors for propulsion methods was born out of Oak Ridge National Laboratory. So last name Bassard. This is one of the first mentions. Does anybody in here know R.W. Bassard or have ever worked with him?
Of him.
Of him? Okay, you've heard of him? Yeah, okay. Yeah, he's got a couple of books out on nuclear thermal propulsion. If you go search around for his name, he was kind of the leading authority on this in the 50s. And so anyway, some of the first mentions of that were here at Oak Ridge National Laboratory, right? And so why were we mentioning these, right? So this is during a time in the 50s when we were looking at more efficient ways to deliver payloads intercontinentally, right? And so we wanted ways to deliver, weapon systems from here to the next continent, right? And so there was kind of a race, a technological race, if you will, between a space-delivered payload and a atmospheric delivered payload, right? So this is basically a race between the intercontinental ballistic missile and nuclear thermal propulsion. And the long story short is they got the intercontinental ballistic missile working first. And so the majority of the funding to support NTP, nuclear thermal propulsion, dropped off, and the interest was largely relegated to NASA after that, right? So NASA identified, hey, from a non-weapons perspective, they were very interested in using NTP, and this is actually a test at the Nevada test site of what was known as the Kiwi flightless bird, right? So this was never intended to fly. This was a ground test reactor that you're seeing right here. In 1959. So why, well, I'll say, what is nuclear thermal propulsion? Again, if you're unfamiliar with it, in general, when you use chemical propulsion, you use a chemical reaction to superheat a propellant, force it through a converging, diverging nozzle, and you push your rocket the other direction, right? Nuclear thermal propulsion is very similar in the sense that you have a propellant, which is typically proposed as a cryogenic hydrogen, a liquid hydrogen, that is plumbed through a reactor system that superheats the hydrogen to the neighborhood of 2800 Kelvin, forcing it out through a converging, diverging nozzle and pushing the rocket in the other direction. So it's not just because that's cool and that sounds exciting and interesting that this was of interest, it's because it is significantly more efficient than typical chemical rocket propulsion methods, right? So for instance, if you wanted to go from Earth to Mars with a chemical rocket, a ballpark number that's always thrown around is neighborhood of 9-month transit at one of your most energy conservative launch periods. Now, you could, using the same mass but of a nuclear thermal propulsion system, reach a higher velocity during that time and thus make your transit shorter, exposing your astronauts to less space radiation in transit. So it's not just that we're impatient, right? It's that we're actually trying to mitigate the total integrated dose to these astronauts, especially for these long duration Martian missions that are now kind of realistically being discussed, hopefully realistically being discussed. And then conversely, you could use less fuel mass for the same flight time. If you were sending a payload or a robotic mission, you could put more stuff on there than you could using a chemical rocket. So it is still of interest to NASA. So now, that was your background on all that information. Now, what am I doing involved with these types of technologies and disciplines? This is my kind of skewed Venn diagram here of my life at Oak Ridge National Lab. So my primary sponsor is the NASA RPS program office in the DOE RPS program. And so I focus mostly on radiation analysis having to do with radioisotope power systems. I do a little bit of work with nuclear thermal propulsion right now. We're pretty much ground to a halt, and we're sort of awaiting this FY's funding to come in, which hopefully will be more than last year's. We'll see, tune in next year to see what happens. But we've got some exciting work I hope that's going to be coming back up to support NTP's developments. And then space radiation, of course, kind of overlaps both of these disciplines, so there's always an element of that wrapped up in the analyses that we do. So as far as the specific activities that I do at Oak Ridge to support radioisotope power systems, the primary focus of my time is on what's known as an integrated product team for NASA's dynamic RPS systems, right? So historically and currently we use thermoelectrics. They are hoping to pivot over to dynamic heat engines, and so we are supporting in a technical capacity they put out a public solicitation. We're reviewing these companies that are proposing these technologies and hopefully kind of winnowing it down to the most successful company, and hopefully within ones of years we're going to be seeing some of these put at least in a technology demonstration level, maybe not a sole dependent power provider, but a tech demo, we hope. Out of that work has been born some modeling tools that we've developed called the radioisotope power system dose estimation tool. And then pretty much whenever NASA calls, I like to pick up the phone because they've always got something interesting. And so they call us semi-regularly to do radiation analysis for various mission scenarios that we'll be talking some about briefly today. Oh, and then I unofficially get to sit as a fly on the wall, kind of solely in a learning capacity for the Mars 2020 Power System team. I have no official tasks other than to sit there and be quiet and listen and take notes, which I love, and it's very exciting to see some of the mechanics behind the scene about a contemporary mission, and I'm very grateful to even be allowed to sit in these meetings and listen. So, dynamic power systems. In 2016, NASA put out a call to industry to say, bring us your brilliant ideas for dynamic power conversion. We got a neighborhood of, it was tens of submissions that came in, everything from totally insane to highly viable, and we quickly winnowed it down to the neighborhood of 5 and started funding these programs. One of the programs, one of the vendors did not make it through the first phasing of the program and has since been winnowed down to 3 technologies. There are a number of papers, if you start to go out and look into this a little bit about NASA's Dynamic RPS initiative, you can start to read in detail about some of these companies, so this is all out in the open right now. Criari is an interesting Brayton cycle, and again, I won't be talking in depth about some of the specifics of these, but just on a high level, this is a Brayton cycle, and these are both Stirling cycles over here between SunPower and American superconductors. And so my role on this has been to look at the radiation concerns, right? So something that's new that's being introduced by these dynamic systems is they have traditionally rad-sensitive components in them. They've got all these organics, right? Which do not like to be close to, kilogram levels of plutonium oxide for decades on end, or exposed to galactic cosmic rays for decades on end, much less Jupiter. The working fluids have gaskets and O-rings. There's moving parts that require rad-sensitive lubricant materials that are being proposed. The converters require permanent magnets in them, of which there's some very interesting phenomenon about elevated temperatures in combination with exposure to radiation. So we're helping to model and understand what types of thresholds we might want to, or might be expecting in real flight scenarios. Then finally, these are reciprocating or rotary motion heat engines, right? So they have sophisticated and delicate timing controllers that can become quite rad sensitive depending on their proximity to the fuel source. So these are the types of assessments that we're performing. Again, what we're doing is performing calculations to inform concerns about margins of certain materials or components that are being proposed. So how do we do these calculations? Essentially what we do is we model the fuel, plutonium oxide, we plug this into our radiation transport or particle transport codes. We build them into the flight envelope as what is known as a general purpose heat source, or a GPHS, and then we, for lack of a better term, we push go and run our simulations. Some of the preliminary calculations that we did, this was not sharpening our pencil, this was kind of the first WAG, first order of estimate, where we would take different phantoms around a notional fuel amount that was being considered for a given mission. We would populate these various phantoms with various materials. There was the neighborhood of 150 or so materials of concern. We would populate these phantoms. We would calculate dose rates. We would integrate these dose rates over notional mission lifetimes to see what the dose from the plutonium oxide alone was. Then we would perform calculations to estimate at solar minima, kind of worst case scenarios. If you remember, during solar minima, you will have higher background galactic cosmic rays and integrate for a notional 20-year. A lot of these mission architectures they're looking at, they base them on a 20-year lifetime. So we'll look at an integrated worst case scenario for 20 years, which is highly unfeasible. You would not, if this were happening to our sun, we've got bigger problems that we're going to have to be worrying about, but nonetheless. We would also entertain solar particle events to look at what a worst case scenario solar particle event might look like to some of these components. And then finally, we'd like to add in a contingent for Jupiter, because these discussions come around. They like to have what's known as a multi-mission capacity for these designs, which means you have to entertain maybe going to Europa, right? So that is encapsulated in this vocabulary known as multi-mission, is going to Europa. So we always like to itemize the fact that they might go to Jupiter. So I'm not going to dig too much into the details here, but what I do want to say is this is the type of information that we would report back to the projects. We'd say, okay, we did a bunch of calculations. Here is what we estimate your worst case scenarios are from Jupiter in blue over here, from your radioisotope power system fuel in green here, solar particle events in blue, and galactic cosmic rays in blue. And with this itemized approach, we like to be able to say, so if you're going to Jupiter, your total integrated dose from all these combined is, you know, the gray bar right here. Whereas if you're not going to Jupiter, going to Mars, something like that, your total dose is going to be, you know, on the order of the black bar over here. And then what we typically do is we overlay some demarcation of some known margin or area of concern for a given material or component, and we can say, okay, you know, you might want to worry about it for component X or component Y. This graph over here is basically the same thing, just looking at particle fluences as opposed to absorbed dose in materials. So this is the kind of reporting that we will do back from a radiation perspective for these types of proposed missions. So what we're doing right now, and I'm kind of excited about, is we really are sharpening our pencil. They have, well, the companies have proposed their final design proposals and system layouts. So this was highly notional as to the system layout, and really what we're sharpening our pencil on is going to be this RPS fuel dose right here. And there's a number of rad-sensitive materials that they claim that they're not going to be able to trade out. So we're wanting to make sure that we want to understand what a worst-case scenario is going to be for those, or at least what we might expect. So other ancillary kind of calculations that we get to do, just to kind of fly over some of these because I think they're kind of fun and kind of interesting. We did a very quick study of looking at what it might take to melt through the ice sheet of Europa. There's a notional 20-kilometer thick ice sheet on this cue ball moon of Jupiter that, in theory, will drop out into a liquid water ocean underneath it. And so if that's all true, you can see that there's a great interest to the fact that there may be some form of microbial life there, perhaps so, perhaps not. We may get to find out someday, I hope. So nonetheless, we were doing some thermal and radiation analysis on the amount of fuel that it would take to effectively melt through, and then the ambient radiation field that you would be generating by that. By the way, it's a massive amount of fuel that you would need to do this. Are you going to be killing the very microbes that that the biologists are wanting to study, right? And so that was an element of this study. I was alluding to the Dragonfly mission that has been named. This is very exciting, and we had some very preliminary high-level discussions with the Dragonfly team when they were selected to look at implications from the radioisotope power system that they are going to be using and how that might affect their neutron spectrometers and gamma ray spectrometers. We also did some calculations for a new and innovative lanthanum telluride thermoelectric material to see what the implications of transmutation might be. There were some irradiation experiments that were performed that produced very small amounts of iodine in the system through transmutation. And so we ran some worst case scenario analyses by neutron irradiation from the plutonium oxide and how much iodine on a system level, worst case scenario, you might make. And spoiler alert, it's on the order of femtograms. Worst case scenario, it's likely not going to be an issue. But that was an interesting, fun study. And then, I know I use the word fun a lot, but I think these are just really exciting and fun projects. And so this is one very recently that we were working on where there's an interest in going to the moon and Mars. And as part of this interest, we've been looking at what pressurized rovers might be pivotable between both the moon and Mars, right? You don't want to revamp a whole system depending on whether you're going to the moon or Mars. They're hoping to buy in and flight qualify one design and use it for both. So they were proposing, the group that I was working with at NASA was proposing to use radioisotope power systems to power this, both for lunar and Martian missions, 30 days inside the habitat notionally, and they wanted to look at what it would look like to have the power system inside the pressurized rover versus out, shielded and unshielded. So, to kind of dive into it real quick, a power system that we've got on Curiosity rover right now has just under 5 kilograms of plutonium oxide on it, right? And you're getting on the order of tens of millirem per hour if you're standing about from here to this case to a fully fueled, fresh MMRTG, fresh fully fueled MMRTG. This analysis was proposing using about 6 of these, okay? The equivalent fuel of about 6 MMRTGs, okay? And they were wanting to put this inside the rover, right? And so it's funny because these are technical groups of people, and it never failed. How many people have seen The Martian? Okay, if you haven't, it really is a fantastic movie, and a fantastic writer too. But nonetheless, so there's a scene where Mark Watney goes and digs up an RTG and puts it in his rover so he doesn't freeze to death. And so everybody in this group kept going, well, they did it in the movies. And I'm thinking, these are like brilliant scientists and engineers. And I'm thinking, and so my argument to them was, the reality of doing this does not map to a philosophy that we in the shielding community try to adopt, that this as low as reasonably allowable. Sure, if you're going to die immediately, then yes, of course, put it in there, get to your lander and get off the planet. But as far as living in there for 30 days with 30 kilograms of plutonium oxide, in my opinion, it's not advisable. Yeah. So this is just to say, these are kind of a look over of the rover and the trailer and our transport models of it. And so this is kind of to scale. This is just some random cropping of an astronaut. This is when we looked at it with the power system inside the pressurized rover versus embedded in the chassis of the trailer behind the rover. Again, I know I'm kind of glazing over a lot of the details here, but I'm just trying to give you a survey understanding of what we looked at. So these are just qualitative looks at some of the dose maps that we made here, right? And so this is the unshielded configuration of the power system inside the rover, the shielded configuration inside the rover. When we map this over to keeping it outside the rover, unshielded versus shielded, the long story short is the bluer the color is getting here, the better off you are as an astronaut. But quantitatively, if we just wanted to look at, so spoiler alert, I don't recommend keeping the power system inside. So when we want to look at what it looks like to keep the power system on the trailer, the two different trends here, the green is if we were to not use shielding at all because they wanted to see what mass constraints they were going to be held to and how much we could get away with, versus kind of a quick optimization of some water shields. They wanted to use in situ shielding materials. Turns out Martian regolith is not that great to shield against neutrons, which is the primary component of your dose deposition from this type of fuel. So this vertical line you see right here through these geometries corresponds to this vertical line on the plot. And our goal was to have this space background dose rate roughly reflected to where we would beat the dose down from the radioisotope power system to the neighborhood of background space radiation. And so we achieved that with really by not taking a long study about optimized shielding. We just wanted to demonstrate that quite quickly, yes, we could make this reasonable. That was the point of this exercise. So I think this is kind of important and interesting to look at. So when we take some of the currently published NASA dose limits, which by the way are kind of being revamped as we speak right now, this is what I wanted to show the team, that the dose, 30 days in a shielded configuration with the power system on the rover is on the order of 1s of rem, all right? This is in my opinion at least, this was a quite reasonable number that we were looking at. Now, and I'm not even going to spend significant amounts of time talking about the sheer fact that if you go to Mars and come back, you're already perhaps exceeding some of the career limits that are published, some of the lowest career limits that are published for NASA. This is part of why things are being revamped right now, is to really assess the validity of manned missions to Mars. But nonetheless, this just shows that, wow, RPS accounts for about 1% of your mission architecture dose when going to Mars, and about 1/4 of your total dose when going to the moon. So, in short, I said, I don't think it's a good idea to have the power system in the rover. And sure, it's kind of reasonable, but we should sharpen our pencil a little bit if we really want to optimize the shielding for outside the rover. So all of this sort of began an effort for us to develop tools for modeling radioisotope power systems, because we're not the only group that is doing this. There's a few different groups at labs, at a few different labs and at NASA facilities that do this. And so some people argue it's easy, you don't need tools, you just draw it up, you drop it in space, and you run your simulation and calculate the dose. I would argue that there's a number of variables that we all agree on in the community that we should make it easy for all of us to turn and intercompare these simulations together, at least was my opinion on the matter. So for instance, the plutonium assay can change from mission to mission, even within flight specs. The impurities in the fuel can change, the age of the fuel will change, depending on where you are in the mission. All of those things affect both the neutron and gamma ray spectra. Where do you put this, right? Are you looking on Earth? Are you looking in space, on the moon, Mars, rovers, spacecraft? And then what type of power system are you using? And how much fuel is in it? So we wanted to be able to turn the knobs on all of these. And then finally, what are you calculating? Are you worried about dose to humans? Are you worried about dose to electronics? So what we call fluence to dose conversion factors, we wanted to have those kind of baked in there as well. So other people interested in these types of assessments could easily turn all these knobs as well. So thus was born the radioisotope power system dose estimation tool. So this tool allows you to choose from a pre-populated library, right? There's only so many flight-qualified radioisotope power systems that have ever existed and will likely exist in our lifetime. So we tried to capture everything reasonable in a typical flight envelope that you would see. And then there's only so many places that you're going to find a radioisotope power system right now. So there's luckily kind of a finite amount of environments and radioisotope power systems for us to entertain. But that, with all the combinations of fuel types, ages, so on and so forth, you know, can allowing you the freedom to mix and match those can provide large amounts of combinations. You know, this billion number, you know, I mean, don't read into that too much. There's a lot of combinations that you can make with this. And then some of the knobs, like I was showing you and why these are important, is because the aging effects of the fuel affects both the neutron spectra and the gamma ray spectra. This is just sort of scrolling through a little random number generator that's populating some of these impurities just to make a pretty little graphic. But nonetheless, you can turn all these knobs to change the plutonium composition or the impurity compositions in there, which also affect the neutron spectra. And then what can you do with it? You could, for instance, compare different radioisotope power system designs, the amount of fuel you've got, the age of the fuel, different environmental effects of the fuel, and then you can quickly intercombine all those variables to look at both what the environmental and aging effects are for a given mission architecture. So, you know, this is just some quick visuals of what it looks like, you know, when you take the same RPS and put it in a different mission environment. And so what does it look like to interact with this software as a user? This is what it looks like. It's a graphical user interface that allows you to go in and pick from your library of geometries. You can pre-populate your input decks. What is this actually doing? This is writing an ASCII input file into a particle transport code that we use that's called Maverick, which is a subset of the SCALE suite. I don't know if any of you are familiar with SCALE, the nuclear modeling suite that's developed at Oak Ridge. But nonetheless, this is writing inputs for a Monte Carlo particle transport software, just in a digestible format to perhaps non-nuclear engineers. Part of the effort here was to make some of these calculations available to teams that wanted to do a quick and cursory first pass study, but not have to come and pay an arm and a leg for somebody at Oak Ridge to do it for them, right? So we can come in and help them when they really want to start honing in on mission specifics, but to get the first order estimate, this is something we hope that is going to help people to do that. So, and what was kind of born of that is this is just sort of fun. We've been playing around with new ways to visualize a lot of spatial radiation data by taking the simulations that we run in SCALE, mapping them through this video game software. We've got some expertise in our near our division where you can actually upload CAD geometries, and then you can map your simulation on top of the CAD geometry. And of course, this is kind of a qualitative way that we use to communicate in some of these interdisciplinary meetings that we have with a lot of aerospace people, where we say, hey, you know, this is what you're looking at. This is what's going to happen. These are things you need to be concerned with. So radiation analysis We have done some modeling, validating, and comparing of different transport codes specific to Martian surface environments. We've also just recently been deemed selectable, which I'm really excited about. I don't like to get too excited because we still may not get this, but our proposal was deemed selectable to do some analyses for planetary protection concerns using radioisotope power systems to irradiate portions of a spacecraft or a return sample to prevent backward contamination during return sample missions. And so I don't know. I'm excited. I hope this one comes through. It may or may not. But some of the previous efforts that we did was this multi-agency workshop that we participated with the Southwest Research Institute that developed a detector that's on Mars Science Laboratory. So that's the first high-resolution charged particle on the detector on the surface of another planet, and they wanted to corroborate compare a lot of the measurements that they were making to some of the state-of-the-art particle transport codes. So we got to go and represent Oak Ridge National Lab, actually not using scale. We were using a code known as MCMP6 when we did this. It was a very fun exercise. It was really exciting to get to work with the teams throughout the world. It was an international workshop. So some of the world's experts in space radiation, I learned a lot from them. I was very grateful for that opportunity. Very interesting. And we also developed a lot of tools out of that exercise because it turns out modeling the galactic cosmic ray spectrum is just sort of a leggy, lengthy, tedious process, and there's a lot of opportunity for automation when you're setting up your simulations, when you're talking about all that heliospheric modulation stuff, and you've got 92 source particles spanning 10 orders of magnitude of energy. It starts to be kind of leggy to set these simulations up. So we did a lot of tool development for that exercise as well. And then finally, nuclear thermal propulsion. So again, this is where the least amount of my time is spent. But nonetheless, it's kind of exciting. NASA this year has devoted the neighborhood of $110 million to developing nuclear thermal propulsion. This is a bump up from last year, which was a neighborhood of $100 million. So we're starting to take them seriously. Boy, I hope this continues. It's been kind of a roller coaster, as I've heard, over the past few decades. So we're hoping this will be a continued upward trend. I don't know. We shall see. But nonetheless, the work that we're doing, members of our group have been working with developing a transient system model that couples the rocketry side of the model to the reactor side of the model. And so there's been some INC work that's been going on as well. Some of the INC work that is currently going on is developing test beds for irradiation experiments. So this gets kind of fun and kind of exciting here, where we have what's known as the Tin Man, which was kind of the prototype precursor to Iron Man, which is going to be an in-core hydrogen environment that will heat instrumentation and control components to operational temperatures while undergoing hydrogen flow. So it's like, kind of an exciting experiment. Again, I'm not an experimentalist, so I get to go, golly, that sounds really crazy. I hope you guys are successful with this. But the point of this is the measurements that they're going to be making about the degradation effects of the INC that's being proposed for the nuclear thermal propulsion systems will feed back into the models that we are working with. And so this is kind of a deliberately ambiguous slide set here, and so I apologize. We are told that we can show pictures but no numbers. So these are a bunch of graphs showing a bunch of stuff about some modeling things that we're doing. I've really been enjoying, and I'm not a system modeler, so I've been really grateful to get my feet wet with looking at the interdisciplinary modeling efforts between the aerospace and nuclear engineering sides of the house. It's been a lot of fun. We're working primarily with Marshall Space Flight Center on this. So tune in, next year. We hope to have some more good news about the developments of NTP and its relevance as we're talking more and more about the moon and Mars. So that's it for the contemporary stuff that I'm involved with directly. I'm sure a number of you all may be familiar with some of the other historic projects. For instance, the SNAP Systems for Nuclear Auxiliary Power. Oak Ridge National Laboratory had a large slice of the pie during the development of this effort. The SP100 reactor program was very interesting. The Jupiter Icy Moons Explorer, I know a few people here have already mentioned that they were part of that effort when it was at Oak Ridge National Lab. And then very recently, the Advanced Stirling Radioisotope Generator, or ASRG, a large portion of analytical work and irradiation work came to Oak Ridge to work with NASA on the development, kind of one of the first iterations of the dynamic power conversion evolution that came through the lab. And then I'd be remiss if I didn't mention, of course, the PU-238 project. I work with a lot of the members of this team. Very exciting, the sole provider of plutonium oxide right now to the nation's RPS fleet. So we want to keep HIFER up and going and everything good. So the RPS program can be successful, and they're doing a phenomenal job at doing that in the PU-238 program. The materials that encapsulate the plutonium oxide, the cladding materials, which I brought a case in today. This is our show and tell case right here that we're allowed to bring out. Please don't pick the plexiglass up in it. You're not supposed to touch the physical components themselves. So just leave the plexiglass on it, but I'll open it up when I finish here in just a moment. And I invite you to come up and check it out. It's very interesting. These are all fabricated at Oak Ridge National Laboratory. And then thermoelectrics, there's a lot of work being done at the lab to support NASA's initiatives on analyzing new and innovative thermoelectric technologies. So this is kind of the, not required reading, but my recommended reading. If you're interested in nuclear power in space, snap a picture of the screen. These are just, a few papers, a few books that I would recommend, a few videos that I would recommend. Again, focusing on radioisotope power systems, space radiation, and nuclear thermal propulsion. And if you're interested but don't get to snap a picture, just come up after the talk and I'll show you whatever it is. See a couple people snapping a picture there. I'm about to flip. Get it? And then, finally, your recommended reading right here. So there's a handful of databases. I'm sure a lot of you are familiar with OSTI, of course. But nonetheless, the NASA Technical Report Server, I spend a lot of time digging around in there. Fantastic source of very interesting historic and contemporary papers having to do not exclusively with nuclear stuff, but just any published papers through the NASA infrastructure goes through there. And then a few books on all of this and a handful of papers that I recommend. And then finally, this is my shameless plug. If you are interested in the nuclear space technologies and communities, there's a very exciting conference that's coming to Knoxville this year, and so we are hosting it. And I'm on the organizing committee. This is my conference. I love this group of people. These are not pie-in-the-sky people. These are people that are working right now on funded projects that are nuclear space related. So it's the Nuclear and Emerging Technologies for Space, April 6th to the 9th. At the Downtown Convention Center. It's closed for paper submission at this time, but if you want to attend, you can sign up. There's a registration link on the webpage right here at nets2020.ornl.gov. I recommend everybody come check it out if this is of interest to you. And that's it. That concludes my talk for today. I really thank you all for coming out, and I hope you enjoyed that information. Yeah, Bruce. Yep. Yeah, no, that's a good question. So Bruce Patton, a colleague of mine from Oak Ridge, was just asking about ATR, the Advanced Test Reactor at Idaho National Lab. So it's a good question about plutonium-238. That number that I put up there, 1.5 kilograms per year, includes using ATR as part of the production stream. So I don't know the exact numbers about who or what percentages are going to be split between HIFER and ATR, but I have been told that the 1.5 kilograms a year will require ATR to be online.
They're not making anything right now, are they?
I think I'm not willing to say. I'll say that. I'm not sure. I don't think they are, but I can't confidently say one way or the other. Yes.
Yeah, have you looked back or gotten any lessons learned from the nuclear-powered aircraft?
Yes, I was just reading. Yes. Well, okay. Yes. Unrelated to anything I talked about today, there's been some projects I've been involved with that are relevant to that past project. And yes, I last week was just digging around reading about that. A really fascinating project, very exciting. And so some of the tests, so that program was looking into a nuclear-powered, an atmospheric aircraft, right? So you could fly a plane around with a reactor. And some of the tests that they did, oh God, was it a B-36? I forget. There was a plane, a B-36, where they put a reactor in it, not to power the plane, but to build a shielding configuration for the pilots to see if it was going to be just wildly untenable to fly these people around. They flew like 50 or 60 flights, something like tens of flights. But,
and they operated a tower shielding facility.
Yes, yes, yes. And so I've been reading
and
about
we had a SNAP 10A at tower shielding.
yes, yes. This is all true and very, very cool. Yes. So that reactor that was flown around, apparently they found, and correct me if I'm misspeaking here, okay, I'm relying on you now, but from what I read, they were saying that they did find that it was a little too untenable. The dose was going to be untenable for the massive shielding they could put in the cockpit. And so they furthered the studies to tower shielding facility where they could say, okay, we're not going to fly these poor people around and irradiate them to death. We're going to do these atmospheric, 300, 100-foot tall atmospheric irradiation tests. Very interesting. I've heard that tower shielding facility, like I guess one of the cables broke or something recently in some storm, and they're talking about bringing it down now. I don't know if that's... I don't know. That may just be wild hearsay. No, probably shouldn't say that. But yes, and thanks for pointing that out. Yes.
You mentioned something about the aging of the fuel. I don't remember offhand what is the half-life of plutonium-238. Is that connected with that?
Yes. So 87.7 years is the half-life of plutonium-238, which is the primary isotope in plutonium oxide fuels. And so what do you see with aging? So so neutrons will die off. So So your alpha emissions are what drive the heat generation of the fuel, right? And so that's going to die off with the half-life of plutonium-238. The external dose concerns, though, is a little bit different because what escapes the fuel, right? The neutrons from spontaneous fission and alpha-N reactions with the fuel, right? So those both die off with the half-life of plutonium-238. However, gamma rays that escape, fresh plutonium oxide fuel is relatively benign from a gamma ray perspective, but as the decay chains build up, you start to get thallium, bismuth, and lead isotopes, which have like a 1-ish, 1.5-ish MeV kind of gamma signature that starts to build in. So around 18 years or so from fresh plutonium oxide fuel, your gamma dose will actually increase, and then it all starts to fall off together following that 87.7.
Can you give examples of the thermoelectric materials they use for the...
Yeah, so like bismuth tellurides, lead tellurides, those are from the silicon germanium, and then these lanthanum tellurides they're looking at. There was a program that, I think it's, I'm not sure.
They are paired, you said.
Correct, yes. So there will be like so I'm not a materials guy, so I don't want to go too far out on a limb here, but there's an N-type and a P-type material that you set up in parallel across your temperature differential, and that's what drives your voltage buildup. Materials people, is that right? Is that, I don't know.
Mike?
I'm sorry, yes.
Are you going to give us a quiz now?
Yes, yes, there will be a quiz issued, yeah.
Dose reconstruction has a long history from going back to the Japanese bombs and then reactor, anything that emits radiation.
Yes.
And you've advanced things a lot, apparently, in the notion of space. Do you know if there's been any feedback to the dose reconstruction people who are working on the terrestrial issues?
Okay, so what I can say to that, so we are not informing anything about the viability of the claims of those from space radiation. We're using the information that teams like the ICRP and NCRP, which develop these quality factors for neutrons and other particles and implications biologically. And so we kind of take their latest and greatest information and make sure we try to represent that accurately in our models. And so what I can say about space radiation is there's been a lot of work that's done at Brookhaven National Lab, NASA Space Radiation Laboratory at the RIC Collider, where they take heavy ions, and I'm trivializing their work here, but they irradiate mice and then study central nervous system effects of the mice as a function of galactic cosmic ray irradiation. And they are providing really the bleeding edge right now of the effects of space radiation long-term exposure to space radiation. And it turns out one of the more significant effects they're seeing is central nervous system effects. So I don't know, that's been some interesting, I don't know if that answers your question.
Yeah, that's
or
the
not.
sort of thing I was asking.
Yeah, and so, right. And so for instance, there's quality factors that team have been developing specifically for heavy, high energetic charged ion irradiation, which is kind of a new concern. You know, there's the accelerator community and the space radiation community, and that's about it. They care about that type of radiation. So they've really been pushing the envelope about understanding that better. And so we take their information and make sure we map that hopefully correctly into our models, right?
Good.
Thank you. Yes.
Decades ago, our ORNL M&C division had the major role in providing the iridium cladding for the plutonium oxide pebbles. I'm wondering if that's still to some degree relevant or pretty much history.
It is extremely relevant. It's in this box right here. Yes. So this black box. That's my property removal pass. So yeah, it's very relevant. It is crucial and imperative to the sustainment of the RPS program. So this is a flight qualified design. And if you change anything about this, it means you have to revamp the whole qualification process to get to a flight-ready power system. So they've got a good thing, and they're sticking with it, and Oak Ridge is still in charge of developing both what's known as the lightweight radioisotope heater units, RUS, radioisotope heater unit, and the clad vent sets for the plutonium oxide.
The cladding alloy composition is pretty much finalized as something that works.
Correct, yeah.
You're going to tilt that up so we can see it?
I'm going to invite you to come up. I will, yeah, I'll tilt it, but I would invite you afterwards to come and check it out. I find it quite interesting. But yes, there's contemporary work going on, and in theory, as long as the RPS program is alive, they'll be using us to keep making materials.
Thank you.
Okay.
What are the planned power requirements and expectations for the next manned moon missions that are supposed to occur in 4 years or so?
Yeah. So I'll just say, I don't know. I don't know. Right now, there's. I mean, if you ask, like, if you call up NASA and you say, "Hey, I need a radioisotope power system today," there's one that you can use that's ready to go off the shelf, the multi-mission radioisotope thermoelectric generator, right? And so it puts out about 110 watts electric at beginning of life. And so I'm not willing to comment about what may happen in the near future because there's a lot of different vying projects that I don't want to stir anything up. So, you know,
what's the planning time frame though? If the mission's going to happen in 4 years, don't they have to have this planned by now?
These are great questions that I'm not willing to comment on. But yes, I'm interested as well to see what happens. And I think I expect everything to be successful, but I don't know about which way it's going to go and which power system they're going to use.
The one slide where you mentioned Tin Man and Iron Man.
Yes.
Are those actual tests that are going to be conducted out west?
No. So the group that is doing that work have demonstrated the effectiveness of definitely Tin Man. So these are built. They're physical. We've got them in a lab over at the lab, and Tin Man's been run at Ohio State University's reactor. And Iron Man is designed to also fit in the test tube that they've got at the OSU reactor as well. Okay. I'm not sure. I think they did some tests with Iron Man thus far, but they haven't moved to the point where they're flowing hydrogen through the test bed yet. That's kind of the next step. So the first round was, drop it in there, run a couple tests, make sure everything doesn't fall apart. And so again, I don't know the specifics on that right now, but I know they've tested Tin Man. I think they've tested Iron Man, and the evolution will be to get to a point where they've got flowing hydrogen while it's in core.
It took many years to get approval with the coal source in Haifa, which is flowing hydrogen.
Yeah, right. So we've got a volume.
Put that in a DOE reactor would be an interesting project.
I agree. Yes, and so this team works regularly with Haifa to do irradiations, and where we're running up against right now is volume constraints.
Yeah.
We're putting in some big stuff, relatively big stuff, so we need these bigger test tubes to drop them into. And so OSU is a place that we have a relationship with that they're using currently.
Good. Very good.
I think we're going to maybe allow one more question, but then you can come up and talk to him. We need to start clearing out of here a little bit. So one more over here.
The fellow behind the column has been trying to ask a question.
It's a quick one.
Oh, okay.
So what kind of materials are you being modeled for your shielding, and are there exotic shielding materials in the future?
Yeah, right. Yeah, so I mean, that's a very good question. In the short,
It was amazing, absolutely amazing to see from that distance what was going on. And then a later tour of the facility showed the tank of liquid hydrogen, and it was enormous. Occasionally they'd blast off the shot, and it was pretty interesting to see.
that's really special that you got to see that. I mean, that was an incredible engineering feat that we're never going to see reperformed in the way that it was at that time, you know. And so that's really special that you got to see that. That's interesting.
Okay, well, thank you.
Thank you all. And you're welcome to come up and look at this if you'd like.